people. We're broadcasting again from the Stoffler Broadcasting Studio, and now I'm giving you a lifeline for descriptive statistics. That's your third chapter. And being the third chapter, of course, we've got the big three measurements. And those big three measurements that we're looking for, or questions that we're trying to answer, would be the shape of the data, where is the data centered, and how wide is it, or how widely dispersed is it? Is it spread over a large range of values or a more narrow range of values? So spread is often referred to as dispersion. Then we're also going to talk about ways to standardize variables so that we know their magnitude. We're going to look at percentiles and quartiles and just briefly touch on correlation. So the questions we're essentially trying to ask or answer in this chapter would be, how spread out are the data? Is the shape of the data, is it symmetrical, meaning like bell-shaped or a normal curve? Or are the data skewed, meaning skewed to the left or skewed to the right? Where are most of the data values clustered? That's our center. Where are most of the data values clustered? And are there any unusual data values? Unusual data values or outliers? So when we want to know about the center, where is that most data values clustered, we have several measures. The first one is the mean, which is the average. The second one is the median or middle value. That's also referred to as the 50th percentile. Now, I hope everybody realizes an average or the mean in any case is always the same. You just take all the observations, you add them up, you divide by the number of the observations, and that tells you the average value of the observations. The median's a little different. And basically the median, you would take a data set, you would rank it like ascending or in descending order, and then you would find the middle value. Let's say you had 15 data items. The middle value would be the 8th item. That would be the median. If you had 14 data items, well then it would be both the 7th and 8th values that would be in the middle. So you would take an average of those two, and that would be the median. So you'd add 7 and 8, divide by 2, and you'd get the median being 7.5. Mode. Well, mode's pretty easy. It's the most frequently observed value in a data set. Sometimes there's no mode, or some data sets can be what we refer to as bimodal or trimodal. That just means that there are two areas where certain values might occur, or 3 areas where a lot of the values seem to occur. Okay, we'll show you those in a moment. There's another one that I've added. It does happen to be in your textbook, which a lot of the textbooks don't include it, but that's the geometric mean. So again, we're saying that word mean, so that means it's an average. But instead of an additive average, like an arithmetic mean where you just add them all up, get the total and divide by the number and the number in the sample, the geometric mean is has to do with products or multiplication. I promise you, I will not inundate you with formulas. And as far as I'm concerned, any teacher that inundates you with formulas is doing you a disservice. It's not about formulas, it's really all about concepts. So in this one case, though, I am showing you the formula so that I can give you a definition for the geometric mean. And the way we calculate it, what that formula says, it's the nth root of x1 times x2 all the way to our last x value. And then you subtract, after you've taken that nth root, you subtract 1. Now, the geometric mean, what in the world are these x values? Well, these x values tend to be either growth rates, ratios, they might be indices or indexes, or percentages. And the hardest part of the geometric mean is really understanding not so much how to calculate it, and in your lab I've given you a real good example of how to calculate a geometric mean. And I've also asked you to do that in the lab assignment. But what's more important is for you to understand what in the world does the geographic mean mean. Yeah, what's the mean mean? So the question is, or a way to describe it is, if an amount increased or decreased over time by the same constant rate, what would that rate be? You know, it's very, very common to use the geometric mean when you're talking about investments or stock portfolios or the price or value of stocks over time. You know that the growth rate of stocks can be very volatile. It can also be pretty stable depending on the stock you might own. But one year you might have a rate of increase of 20%. The next year it could go up 5%. The next year it could go up 40%. And the next year it could fall by 10%. Well, holy cow, how in the world do you figure out what that average is? You use the geometric mean, the nth root of each of the product of each of those individual growth rates. And you have again that example in the lab that goes through the mathematics of doing that calculation. Now here is another example. This one is done differently, but it's also another way to show you how to do the growth rates. In this case, we've got JetBlue Airlines, and we've got their revenue for 2002, 3, 4, 5, and 6. So what we're calculating is the average rate of growth. We could do each calculation separately. We could figure out like 998 minus 635, that difference, and then divide by 635, and that would tell us the average annual growth from 2003 over 2002. And we could do that again for 2004 compared to 2003, or 2005 compared to 2004, or 2006 compared to 2005. But you can plug the values into the formula. And again, I'm showing this a bit differently than I did in my lab, just to give you another approach on how to calculate the geometric mean. And in this case, we're wanting to know what's the average growth rate over these 4 years. So here is the math. You take the fourth root of this product, and then you subtract 1. And you know, oh, there it is. I do have the answer. It comes out to be the fourth root of this fraction. Comes out to be 1.389. You subtract 1, and then you get an answer of 0.389. Turn it into a percent. Slide that decimal place 2 places to the right. And you get that the average rate of growth for JetBlue Airlines was 38.9% per year. Now, we did not calculate each individual growth rate here, or I didn't show that, but those would be very different from one year to the next to the next. So this whole idea is to say, okay, if JetBlue during the year 2002 had revenue of $635 million, and every year their revenue increased at 38.9%, then for the year of 2006, their revenue would be $2,363 million. So again, we assume that it grows at a constant rate based on the actual growth rates. So what we're trying to do is kind of find an objective way to take all those different growth rates, which can vary significantly from year to year, and show what they would grow at if they had grown at a constant rate each year. Okay, so shape of the data. Well, the shape, when we talk about shape, what we're interested in, is it symmetric or is it skewed? When we talk about being symmetric, what we're talking about is it normally distributed? Is it a bell-shaped curve? Or is it skewed, meaning is a tail longer to the left or longer to the right? So are we looking for data distribution that has more values to the left or to the right? Or is it more symmetric with a fairly even number on each half? So one way you can determine the shape of the data is by comparing the mean and the median. You can also look at a histogram. That's a real easy way. You know, we did that in the last lifeline. We had a histogram, I think that was bimodal or trimodal, one of the two. Then we can also look at something called the skewness coefficient. Now these are 3 examples of data sets, this first one in the middle is symmetric. The mean, the median, and the mode all happen to be the same. Well, that's very unlikely that that's ever going to happen. Hopefully, the median and the mean are very close to being equal. If they're not, though, if the mean is to the left of the median, then the data are skewed left. When we say skewed left, we're talking about a fact that this tail points to the left. So there's a lot of data values toward the left side of the mean. And so again, that's a skewed left distribution. When the median is to, or the mean is to the right of the median, then we would say that those data are skewed to the right. We've got this long tails tailing off to the right. So skewed right or skewed left? Well, we have a measure that we can use, which is called the coefficient of skewness. And the coefficient of skewness, without just having to look at a histogram or plot the data, it's a measure that Megastat will give us. It ranges from -3 to +3. If we get a negative number, well, then that means it's negatively skewed, meaning skewed to the left. If we get a positive value, that means it's positively skewed, skewed to the right. And what we're looking for or hoping for is 0. Not exactly 0, but very close to 0. If we get a skewness coefficient that's very close to 0, it means it's about bell-shaped or about normally distributed. If a skewness coefficient is greater than or equal to 2 in absolute value, that means that the data are significantly skewed. So hopefully we won't see too many skewness coefficients that are in excess of 2, positive or negative. Then there's one more measure that we can use to denote shape, and it's called the kurtosis coefficient. And kurtosis has a few kind of strange words. Kurtosis itself is a little bit odd, but basically when you see kurtosis, just think, are the data tall or are they short? So as it tells you here, kurtosis measures the relative peakedness, meaning the height or the flatness of a data distribution, and that's in comparison to a symmetrical bell-shaped distribution. And again, it helps us know, are those values more tightly or loosely located around the mean? So again, kurtosis is giving us the height. Is it a tall distribution or is it short and a very wide distribution? For normal distributions, the measure for the kurtosis coefficient is about 0. If you get a positive kurtosis value, then that's referred to as something called leptokurtic. It just means, and you don't have to know these names, it just means that the data distribution tends to be a little bit taller or higher than a normal distribution, depending on the magnitude of the value, how high above 0 it is. If it's a negative value, again, that has a name. It's called platykurtic, and that means that the distribution is flatter than normal. And often when you have a distribution like that, then the tails are a little bit higher, and the whole distribution just tends to be a little bit more flatly shaped. So those are the measures we can look at for shape. Then we come to spread. Spread. Well, spread. When we say spread, we're talking about the variation or dispersion of the data around the center. So we're talking about width or dispersion. One of the first and easiest, quickest statistics to calculate is the range. And all you do is order the data, take the maximum value, subtract the minimum value, and basically that gives you the range the data values occupy. And of course, once you get the range, depending on what the data set is measuring, you would want to know, is this where we would expect the range to be? Are these the values that we would expect the range to fall within, or are there outliers? You know, some exceptional value or unusual value. But so our first measure is the range. The next, to tell us how widely dispersed or distributed the data are, would be the variance and the standard deviation. We're going to do a lot of work with the standard deviation, and in order to get the standard deviation, you actually calculate the variance first, but we don't have to worry about it because Megastat will be doing all those calculations for us. So you get these numbers, whether they're the variance or the standard deviation. What do they mean? Well, the larger the value means the wider or more widely distributed the data are around the mean. The smaller the standard deviation or the smaller the variance, then the more closely packed or narrow the distribution is around the mean. Then there's one more measure, and I'm just going to run over this very quickly. It's called the coefficient of variation. And basically what this formula, and again, I'm not going to be inundating you with formulas, and you don't have to know this formula. You don't need to write it down. The coefficient of variation just takes the standard deviation, which is abbreviated by this S. S stands for standard deviation, and we divide it by X bar. X bar, remember, X bar stands for the mean of the sample. Again, X bar stands for the mean of the sample. And the coefficient of variation is used for data sets that have different units like Celsius or Fahrenheit, or data sets that have exponential distributions. We're not going to be making use of the coefficient of variation in this class. So, why in the world are we concerned with the standard deviation or the variance? And I'm going to just limit that to the standard deviation. And as it tells you on this slide, we know that there is this famous Russian man who gave us this theorem, and what he figured out, Chebyshev, is that for any data set, no matter what its shape is, or no matter how tall or short or wide or narrow it is, that at least 75% of all the observations will lie within plus or minus 2 standard deviations of the mean. Now I just spoke what is written here in notational form. And let me explain this notational form to you. This is mu, and again, mu is a Greek letter. That means the average or mean of the population. This other letter is sigma. Sigma is a Greek letter, and that stands for the standard deviation of the population. So what Chebyshev's theorem helps us to know is for any data set, if we have no idea how it's shaped, we know that 75% of all the observations will lie within the mean plus or minus 2 standard deviations. And what Chebyshev also tells us is that at least 88.9% of all observations will lie within the mean and 3 standard deviations plus or minus. So it's a rule of thumb that helps us know the approximate values of data within a set compared to the mean. Now, unfortunately, Chebyshev's theorem is fitting for any data set, but it's a pretty wide limit. So it's better to use the empirical rule whenever we can, and for the majority of time we are going to be using the empirical rule. Now, the empirical rule, I like to call it the 68, 95, and 99% rule. And what the empirical rule tells us, first, for normally distributed data, meaning data that's symmetric and bell-shaped, the empirical rule says we expect that 68.26% of the data will lie within the mean plus or minus 1 standard deviation. 95.44% of the data will lie within the mean plus or minus 2 standard deviations. And we can expect that 99.73% of the observations will lie within the mean plus or minus 3 standard deviations. Now, this began with telling you that this is for normally distributed data, meaning symmetric and bell-shaped data. For the most part, that's the type of data sets we are going to be working with. And then we'll also add in a future chapter a discussion about something called the central limit theorem, which again will allow us to always seem to fall back on the empirical rule. So I've got a slide here that shows a way to visualize the empirical rule. And as it tells you here, we measure the distance from the mean. Here's the mean of a particular data set. And you can see this very beautiful bell-shaped curve, perfectly shaped bell-shaped curve. And here's the mean, the average. And then we can measure the mean plus 1 standard deviation, and that would be here at this point, or the mean minus 1 standard deviation, and that distance is plus or minus 1 standard deviation. And as the empirical rule tells us, 68% of all observations will fall within plus or minus 1 standard deviation of the mean. Or if you want to say 68.26% to be more accurate, that would be true. But again, we often refer to it as just 68, 95, and 99% rule. So what this is also showing is that if you take the mean, add 2 standard deviations to it, the mean, and to take 2 standard deviations away from it, then this is the area or the range for which 95.44% of all the data observations will lie in a normally distributed data set. And then, of course, plus or minus 3 standard deviations, this is the range where 99.73% of all the data values will lie. Now, we're going to visit that in an Excel example that I'm going to show you. But for now, let me go to the next slide. Now, again, why in the world is the standard deviation so important? Well, I've demonstrated with the empirical rule that why we know that we've got that 68, 95, and 99% of the observations are going to fall. But then we can also have unusual observations. And an unusual observation is one that, as I've defined it here, lie beyond the mean plus or minus 2 standard deviations. Well, just because an observation is unusual doesn't mean that we have a problem. But we might have a problem if we have an outlier. An outlier is defined as an observation that lies beyond plus or minus 3 standard deviations. We're going to talk about how to handle outliers, but for the moment, when you have an outlier or an unusual observation, as a researcher, what it means to you is you better go back and double check the data. Was there an error in entering the data? If it's an outlier, is there some reason that you can figure out why you got this unusual value? If it's an outlier, do you keep it in the data set or not? Depending on what the research is about, you may keep it or you may toss it, but you never toss out an outlier. You always note that you had this extreme outlier and note it in your research. But again, it depends on the type of research that's being done, how outliers and unusual values are determined or handled. Now, in order to determine if a value is an outlier or if it's an unusual value, we have to standardize it. And so you're going to be seeing this for the first time, the z-score, or just the z value. It's often referred to as a z-score. And I think students have a lot of problems with what the z-score represents and getting it through their heads about what it is. And I can tell you, I repeat it many times in class, the z-score just tells you how many standard deviations away from the mean a value lies. So let me just go back for a second. Oops. Sorry, I meant to do a previous. So, okay. A z-score tells you how many standard deviations away from the mean a value lies. Like, let's say this were I own a clothing store. And these are my average sales for the day, each day, daily sales. And all of a sudden, one day, I have a day where the sales are way out here. Well, that's unusual. So how many standard deviations away from the mean is it? Well, I can tell by looking. If this is the value that's 2 standard deviations away, and this is the value that's 3 standard deviations away, and if I get an average daily sale that's right here, well, then that's more than 2 but less than 3. So what the z-score does is just calculate exactly how many standard deviations away from the mean that particular sale days number or amount of sales lies away from the mean. So I'm not going to give you the formula for the z. It's real simple, but all it tells you is, remember, the number of standard deviations away from the mean that a particular value lies. If it's a negative z-value, well, then the observation lies to the left of the mean. And let me return to that again. Any z-values that are on this side of the mean would be positive. Any z-values that lie on this side of the mean, the left side, would be negative. Okay, percentiles, I'm going to just mention this very quickly. Percentiles are just data divided into groups, and we do it in form of 100 groups. If you score, for example, in the 83rd percentile on a test, that means 83% of the test takers scored below you. So the percentile tells you what proportion scored below you or lie below you. If we have deciles, then we're just taking that data and dividing it into 10 groups. Quintiles means we've divided the data into 5 groups. And quartiles means the data are divided into 4 groups. Now, let's see. The mean. Well, the mean. We're always doing the mean, the average. The average is the 50th percentile. So that means 50% scored less than that mean or average. Okay, the last one, I think this is the last one, yeah. The last one is the correlation coefficient. Now the correlation coefficient doesn't exactly talk about shape or center or spread, but what it does is, again, it's to determine are two variables, paired observations, are they related linearly? I have a hard time with that word. Linearly. Are they linearly related? Are they positively related, negatively related, or is there no relationship? So the correlation coefficient, R, has to be in between positive and negative 1. It's a value between positive and negative 1. And on the next screen I can show you. Here would be a correlation coefficient of positive 90. You can see that X and Y are very positively related as they tend to slope upward as the values rise. They both rise. Here we've got a correlation coefficient of negative 0.90, showing that the data are negatively related. They're closely related, but as one rises, the other one falls. Here would be an example of, say, a correlation coefficient of positive 50. Here would be negative 50. I hope you can see that that trend is upward. Here the trend is downward. Here would be a correlation coefficient of 0. Just looks like a shotgun blast. Here's another correlation coefficient of 0, the way it might look. The difference here with this last one is that this shape suggests that there's probably a relationship between the two variables, but it's not linear. So further examination would allow the researcher to know or define how those variables are related. Maybe they're related exponentially. Maybe they're related logarithmically. But that would be another measure, again, in descriptive statistics. Now what I wanted to do is I wanted to run over to my Excel spreadsheet, and what I did was I just pasted in a data set. It's 30 days, and what it is, it's the number of hourly flights arriving at O'Hare Airport in Chicago in marginal weather. If any of you have ever lived in Chicago or been there, You know that Chicago is called the Windy City, and it gets very cold, and even in the summer it can be cold. And so they do face some weather challenges. So this is a data set of, again, 30 days, showing the average number of hourly flights over that 30 days. Now what I'd like to do is I'd like to go to my add-ins. Wow, I don't feel like I'm recording here. I want to make sure that I am.